let's go ahead and get this going this afternoon session. Good afternoon. I'm Jim Spellman, the National Space Society's Washington Spaceport Chapter, and I'm here to introduce your next speaker for this afternoon. One thing that I appreciate is that being a former Air Force officer myself, I have a kindred spirit here in Captain Tom Schaefer from the United States Air Force. Captain Schaefer is the Chief of Cost Engineering for the SDI program at the United States Air Force's Space Systems Division, which is at Los Angeles Air Force Base, right out by LAX. He is speaking on cost engineering, a process which integrates systems engineering with cost estimating. The cost engineering process has been recognized as a significant innovation with the Department of Defense-wide implications. Tom is the recipient of the Air Force Acquisition Support Officer of the Year Award and the Los Angeles Air Force Association's Award of Excellence, going to an Outstanding Junior Officer of the Year. Cost engineering is being implemented on the Brilliant Eyes, Brilliant Pebbles, and Advanced Warning Systems program, as well as other Department of Defense programs, and is a Space Systems Division and Air Force Systems Command initiative. So, Captain Tom.
Thank you.
You have the floor.
Okay, I'm going to quickly go through these charts because we have a limited time here. And like he said, I'm from the Air Force Space Systems Division, and I'm in charge of cost engineering for SDI programs. And I'm not a cost estimator by education. As a matter of fact, when I arrived at the SDI programs office about 5 years ago, one of the things that struck me was the cost estimators were basically clueless of the real technical issues that were driving the cost of the systems that I was working on at the time. And those were the glory days of SDI, where we were working space-based laser and ground-based laser systems. And now we've kind of stepped back from that. The cost issues are just as important as they've ever been in Space Systems Division, and really determines whether or not the Air Force can successfully advocate and execute a program to SDIO. And therefore, my management has recognized that cost is no longer an afterthought. You can't design a system and then throw it over the fence to the cost estimators and have them come back with an estimate and all of a sudden realize that you can't afford that. It's got to be done right up front. And therefore, program management realizes that they have to start understanding the engineering and cost estimating methodologies that all the technical disciplines are bringing to bear, as well as the cost estimators, to get these systems costs down. Yeah, go ahead. Thanks. A little bit about the system that we first really implemented this on. This was the Brilliant Eyes system. And Brilliant Eyes is a mid-course sensor for detecting tactical missiles, as well as ballistic missiles, strategic missiles, coming out into space. And if you can imagine the difficulty of the technical challenge, it's equivalent to trying to see a 25-watt light bulb at the distance equivalent to Los Angeles to Omaha, 2,000 kilometers. And that's a tough technical challenge. And when you're left with a tough technical challenge, the system engineer tends to hand out the requirements and explore the requirement space. Next chart, please. And everybody's got their own view of solving this problem, and they bring their disciplines to bear. I mean, for the Brilliant Eyes problem, we had to track several 100,000 objects. There was birth-to-death tracking. Everybody wanted high resolution, high sensitivity, and then Livermore brought the idea of bringing everything off the shelf, if you could. And everybody wants to have survivable, reliable, launchable, and producible systems. And everybody's got a clear process that they think they know how to do that in their specialty. And when the system engineer ends up pulling that design together and handing the design off to the cost estimators, it's difficult often to arrive at a cost answer that you think you can afford. So next chart, please. We think we have a way that can help that. And a little bit about the DoD acquisition process that NASA may have something equivalent to is that at Space Systems Division on our programs, what happens is the system engineers define a system in a document that's called the Cost Analysis Requirement Document. And that document essentially describes the systems to the cost estimating community, and they do a cost estimate on that and report to an organization called the Cost Analysis Improvement Group. At the same time, the designers are going through something called the DAB, or the Defense Acquisition Board. Now, NASA might have an equivalent process to this, I don't know. But I'm telling you that this is a broken process, because by the time that cost estimate comes out here and someone doesn't like it, your only alternative is to really go back to your specialists and get the design done over again. And what we're saying is, why not spend the upfront time to integrate the design processes of all the specialties with the cost estimating methodology so that when you go forward to the KEG and the DAB, you can take forward an integrated design and estimate so that when someone requests that inevitable change in these highly volatile programs, you can respond to that change extremely rapidly, understanding how that change influenced the entirety of the design. Next chart. At the worker level, I'm just kind of a grunt engineer at Space Systems Division, but at my level, never mind the Washington politics that's going on for a minute. In the old days, what would happen is the requirements would get laid down on us, and we'd go off and run God knows how many engineering models that were spread out all over Space Systems Division, the Aerospace Corporation, our contractors, all sorts of CETAs, or Specialty Engineering Technical Assistance contractors. And those design models would end up with a design and go into the cost models. And the problem with that was no one individual or no group of individuals had any insight into the processes that were driving the systems to the costs that they end up being. And what we're doing now at Space Systems Division that's fundamentally different is that we're asking the engineers to ante up with the process by which they got to their answers, both technical and cost estimating, so that we can build these integrated system models so that requirements come in, everybody can trace through the process that ends up designing the system and causing the system to cost the way it does, and then you hopefully get an insight into how to build cost-effective systems and understand how sensitive your system is to the key drivers of that system. Next chart, please. We think there's some schedule benefits to doing this as well. In the old process, the design would come out, the estimating was done, and then there'd be a review. And what we're saying is let's spend the upfront time to really understand how our designs are coming to be and take those designs, do an estimate on it, sure, and then review that estimating methodology. But once you've built that integrated design and cost estimating model, you can rapidly do excursions, which are inevitable in these volatile programs, especially with volatile budgets. Next chart. Okay, there's some benefits to the engineers. One of the toughest parts of my job is getting the engineering guilds, I'll call them, to release their processes to the system engineering function. People tend to be very protective of the way they calculate numbers. As a matter of fact, I found that they're most comfortable with you coming to them with a question and they tell you what the answer is. If you ask them how they got that answer, they might give you some gibberish and they might tell you how they got it, and you may or may not like that. So they tend to be a little bit protective of that. So what we try to advertise this to the engineers is that they can start getting insight into how their process fits into the overall design process, letting them know what the cost drivers are, helping them interface with the other disciplines, providing a controlled process for influencing the design rather than a chaotic one. I don't know if you guys have ever been involved with integration meetings where everybody comes to the design table and says, me, Bill, I need the inputs from Joe, but Joe needs to have inputs from Bob before he can calculate the inputs that Joe needs. So this kind of goes on back and forth, and there may be several integration meetings before you ever get to a design. This process eliminates the need for that. There's insight into other subsystems and a traceable and documentable model that can show at any stage of the design where the numbers came from, all the way back to fundamental system requirements and assumptions. Next chart. What is a cost engineering model? We've kind of synthesized the design tool, the system description document, the cost analysis requirement document, and the cost model all into one tool and provided that tool to whoever wants it. If Bill over in, say, the attitude determination and control area wants to understand how his design issues are influencing electrical power, he can have the models. And he can rapidly understand those models and appreciate his interaction with that other discipline. It takes a lot of engineers and estimators to do this, but once you've got it, you're left with a very complex and highly integrated tool that provides a tremendous amount of insight into actually where the design came from and how it's influencing the cost estimate. Just so that you don't get the wrong impression about this, cost estimating is actually a very minor part of the overall cost engineering process. Engineering tends to be the key of it. And this is typical of the Brilliant Eyes cost engineering model right now, which we have delivered to the concept definition contractors on the Brilliant Eyes program. Rockwell, TRW, Lockheed, and I think Martin Marietta. So this model was delivered to the contractors, and what we've told our contractors is, your answer, the number, is not as important to us as the quality of the process you bring to bear to get that number. Now, if it was just your private capital at risk, and there was a lieutenant colonel and a major managing your program, and we would not pay you if that system worked, maybe we wouldn't be concerned about the details of the process by which you get to your answer. But the fact of the matter is the government's left with a tremendous risk and a stake in the success of a program, and there's a lot of volatility, so the government really needs to understand how the contractor's decisions are influencing that design. And we've found that the contractors being aware of that, the system engineers of the contractor helps them out tremendously as well. Another advantage of this is that I can sit down with a program manager or the chief engineer on a program and literally lead them through any set of logic at whatever level of detail or abstraction they want to understand that issue at. And if they want to understand it in tremendous detail, the model has it there for them so they can understand. A little bit about the logic that we applied to the Brilliant Eyes program. We started with mission requirements, things like threat and technology status and cost, and had our engineers in the major disciplines, the optics and the focal planes, the communications, processing, etc., tell us how they were going to get to the design of those subsystems and lead us through that logic so that we could code them up in this model. And then got the supporting subsystem people to do the same and built this logical hierarchy. I really do hope that some of you will stop by my display over here with the computer and see how we've actually done that on some of these programs. And then out of that design modeling process come various pieces of information that might be of interest to the cost estimators, like how many focal plane pixels are there on the focal plane array? What's the weight of some subsystem? What's the power of it? How many MIPS does a processor have to generate? All these parametrics can go into understanding the cost. Since you have the performance up in this earlier part of the modeling, you can start really understanding your cost performance trades. Okay, the cost engineering tool that we're using is a software package called Javelin, which breaks the classic spreadsheet paradigm. It makes people focus on the process rather than the numbers. When you look at a spreadsheet like Lotus 123 Excel or Quattro Pro, what you see is a matrix of numbers in front of you. We believe that view of information is fundamentally broken for anything but really kind of trivial analysis. What Javelin does is you assign an English language name to every value that's out there, and you relate those things in a hierarchical tree structure so that you can go through the logic very closely. As a matter of fact, I would claim that there's really only one person who understands a very complicated worksheet, and that's the person who wrote it. And even they don't understand how it works after a couple years. In fact, after a number of field mods have been done, that one expert might be off running that tool, and he doesn't know the details of how it works. And everybody's depending upon that person for the answers that are coming out of it. Well, that's a very dangerous situation. As a matter of fact, I've decrypted a number of these worksheets, and I have yet to decrypt a 100 kilobyte worksheet or more and find significant, and not find significant errors in that logic. So what our tool does is it helps us do these design and cost trades. Because it's English language and because all the logic is laid out very clearly, it gets away from the smoke and mirrors that one often sees and how numbers are derived. And like any computer model, if you've got garbage in, you're going to get garbage out. But rather than just smelling that garbage because you don't like the number, you can go in at whatever level and understand the logic or the assumptions that drove that to be garbage in your mind. It's easy to learn, implement, expand, and use. It's got all the features of modern software, and I won't go into that. One of the advantages of this software is that it creates a central information base of English language equations and lookup tables, etc., that allow you to see it from a variety of different directions. One of them is the equations themselves. Another is the tree diagram that shows you where a variable is coming from and where that variable is influencing the system. And then there's pie charts and also explanatory notes, which is absolutely important in these models, is we can write text associated with each equation that says, Bill Smith got this from this AIAA paper, and it's assuming the following conditions, so that when someone else sits in front of that model, they can understand the context that that person came up with that relationship in. And this is a little tree diagram structure I just laid up here. If one imagines a center variable being something like, say, the size of the solar array, and that variable over there being, say, the number of watts that one needs, and that variable right there being the number of watts per square meter that a solar array can generate, you can see how that variable traces back through a whole bunch of detailed logic all the way back to fundamental system requirements, and that number of square meters there might influence the weight of the solar array and the cost of the solar array and a whole bunch of other important system issues, like maybe the weights of the drive motors, etc. And all that logic is laid out in that very clear manner, and I hope you do stop by my computer and let me show you some of that. Implementing a process. There are some cultural barriers that really need to be broken down if this is going to happen. And we've succeeded in doing this primarily because we fought the bureaucracy at Space Systems Division, and they now have a physicist by education and engineer by commitment in the job of head of cost estimating for SDI programs. I'm not a cost estimator, I'm a cost engineer. And that's fundamentally different than most other program offices at Space Systems Division. I report to the system engineer. I don't report to some MBA budget type. And that way, engineering issues are allowed to control the design and the cost estimate of that design, which is really where it ought to lie. Engineers must be part of the cost estimating team. I've become part of that. I've started learning about cost estimating. I've got a number of cost estimators reporting to me. The program managers are ultimately responsible for a cost estimate, but how can someone have responsibility if they don't understand the process and the assumptions that led to something? And what we're offering that program manager is the insight that he needs so that when he makes a decision, he'll see how that decision influenced the cost estimate and the design. We've got an easy-to-use framework and it's available now. That doesn't mean that it's easy to do. I spend like 90% of my day getting engineers to tell us the process and coding up that process and interacting those processes with other ones that we already have. So it's by no means an easy job. I won't go through this chart in detail, but this is kind of your roadmap to building a cost engineering model. And so you've got a number of things that the engineering folks need to be doing, and a number of the things that the cost estimating folks need to be doing. And then once you've got those things in place, you can build one of these integrated cost engineering models and really allow yourself a tremendous amount of insight. And also a very centralized, distilled piece of information about the program that can be handed out to anybody, so no one can claim that they don't know where a number came from. There are some cultural barriers that get in the way of doing this, and I don't want to get in this chart in too much detail either. Suffice to say that there are a number of paradigms that we as engineers or we as cost estimators need to break in our mind, and we've started doing that at Space Systems Division. Next chart. Okay, I don't want to talk too much about process control, but for a long time, the blue-collar world has accepted industrialization, and that they've gotten into controlled processes that are very well understood and managed. But the white-collar world, for some reason, has this kind of art flavor to how it does its job. There aren't really controlled processes in how people interact. And what we're saying is, if we're going to be able to get answers consistently and be able to explain those answers, we're going to have to control our processes. Next chart. And a little bit about what a controlled process versus an ad hoc process. And I would claim that the majority of processes that go on in the engineering, especially in the design world, are essentially ad hoc. And a very good system engineer and a very good program manager can balance all those ad hoc processes and come up with a good product. But there is probably a better way to do that, and that's controlling the engineering and the design process. And you can see, let's just go through a couple of these. An ad hoc process is understood and executed by an expert uniquely for every product. That's just the way guns were made in the 1830s before we started seeing the industrialization of it. And a controlled process is developed and documented by an expert to address a class of products, but it can be executed by anybody. And that's what we've started doing with our design models, is once we have this model from the expert. Okay, I'm going to move on a little bit quicker here. I've got 5 minutes. Okay, and once you have these design models, those models can be shared amongst a variety of system program offices, as well as being provided to the laboratory folks so they can understand where we stand with the use of their technology, how it's influencing the design of our systems, so they can bring to bear better technology to really drop the cost of our systems. Okay, there's a number of things that one would like to be able to do to change our work habits and our view of how we do engineering and cost estimating. And I can't get into these because of time limits, but one of the ones that's important to me is new tenants. What people say inside their heads when they're doing their jobs. And so an example of an old tenant, I'll just do the first one there, is the old tenant says, give me the requirements and the funding and let me go do my job. If the requirements change, we'll have to go back and revisit everything. My customers have no idea what these changes do to us. Now, who doesn't believe the requirements are going to change? Who doesn't believe that the cost estimate isn't going to be in sync with the budget sooner or later? Well, if we say to ourselves, the requirements and funding will change, if my process is controlled and automated, I can rapidly adjust to these changes, and part of my job is convincing my customer where the affordable requirements are. Okay. Where are we with cost engineering at Space Systems Division now? We've got a very mature, brilliant cost engineering model, and I can't say enough about the quality of work that our contractors are bringing to bear on that. It makes some of our early models trivial in comparison. The cost engineering models are being developed for Brain Pebbles, and TMD stands for Tactical Missile Defense. SSD and Air Force Systems, Space Systems Division and Air Force Systems Command have initiatives that are underway. There are some potential issues by the review folks not being comfortable with this because the review people back in Washington are uncomfortable with the engineering side of it. And then we've got support internally from our office that handles cost, which is a major breakthrough. They've kind of adapted to this paradigm shift. And then we've got some other potential issues, and that's that the contractors may view their design logic as proprietary, and we understand that, and we've started making a relationship with them that will allow us to have access to that. We've got a number of design models already available and being worked in a variety of different areas. We're using that on multiple programs. It's snowballing now. The Brilliant Eyes processing model, for example, which assumes a GVSC chipset, is being used on the Fuse model, and that's just an example where these things can be shared. The electrical power model, by the way, is also being used on both programs. And there's a variety of things that one might want to get out of this, but the bottom line for me is a mutual understanding and support of the design and cost estimate, so that everybody on the team knows where the numbers are coming from. And in summary, resource constraints are highlighting the importance of this to the Air Force. We've got a process online approving. We just had the Space Division system engineer come down, and he was going to spend half an hour with us. He ended up spending 3 hours with us and is very fired up about this. We've got a groundswell of grassroots support from the engineers and the cost people who have really learned the kind of insight this can provide them, and it's changing the way we do business at Space Systems Division. And I hope I can say to General Graham someday, hey, you can go to Space Division and have a program done affordably out there as you can at SDIO. And that's the end of my talk.
To an Air Force officer who's under pressure to bring it in under time. We actually have about 2 minutes worth right now that we can utilize for answering any questions. So Tom, go ahead.
Yeah, okay. Yeah.
Are you available to come talk and contract?
I'd love to do it. We're not only available to do that, we would be happy to share our engineering models as they stand. Those models were developed by Aerospace Corporation professionals. As far as we're concerned, they're in the public domain, and we hope that people will use a starting point for even further refinement. Those models are very easy to start catching on to and understand, and some of them are generically useful across programs. For a matter of fact, for Space Station, for example, we've got a model for the control moment gyros to size and weigh and cost estimate those that might be very interesting to you. Taking things like the amount of torque, momentum storage and torque requirements, and your slew rates and the mass of the vehicle, etc., and being able to figure out how big those things are. And we've actually tied that into a lookup table from Bendix and Honeywell of the available control moment gyros to see if you can fit with any of them. Now, you guys are big enough that you need your own, but the Satellites and Space Division, for example, can choose from the list.
My understanding is that the requirements change, programs and peer rates and issues your answer.
That's exactly right.
That would imply then that due to the parametric requirements, assess the program
so that they're affordable. Exactly right. Now, the software we're using right now is Javelin, by the way. Now, the problem with Javelin is that the logic only goes one way. You set all the requirements and the assumptions, and it calculates the design and the cost. We're going to implement our cost engineering models, which are essentially an ASCII list of equations, and then Javelin converts it into all these neat views. But we're going to start porting those over to more sophisticated tools that'll be able to do things like back chaining, so that you'll be able to specify a cost and allow a few parameters to float so that you can get to that cost. Or optimization. The tools that we're looking at to replace Javelin with will allow us to say, okay, here's my objective function, play with these variables and optimize them such that I can get to that objective function, whether it's a weight constraint or a cost constraint or some other constraint that people have defined. It's no panacea. Getting that logic into these models is real hard work, and getting all that logic from the various disciplines to sync up so that they give you a good system engineering model is real hard work as well.
One more question.
Does it know anything about schedules? It seems like some chunk of that.
In fact, it does handle time. Every variable can inherently have a time associated with it. And so, for example, we've gotten to the point now where we take the features of the program and allow it to spread our costs for us as a function of schedule issues. Now, we haven't started doing that as sophisticated as we'd like to, and if I had more time, I'd talk about the entire integrated product development effort we have out at Space Systems Division, where we're taking integrated master schedules, performance models, cost engineering models, a whole bunch of things, relating them to an Oracle database and having everybody be able to share information across a wide variety of tools, not only these models. So if I had more time, I could answer that question in more detail.
For those who do have additional questions, Captain Schaefer does have a display out in the hallway, which will be here for both today and tomorrow? Is that-
Right, that's correct.
Okay,
We'll be here.
so the captain will be available to answer any of your questions.
And those people who are interested, please get a copy of the paper.
We thank you for your time.
Yeah.